Hello and welcome back to Introduction to General Relativity. In the last lecture, we introduced Einstein's field equations, and in today's lecture, we're going to continue our study of Einstein's field equations, commence the study of their solution, but only in perturbation theory at the linearized level. So if you recall, in the previous lecture, we introduced the following equation. RAB minus a half R, the Ricci scalar, times GAB, the metric, is equal to 8 pi TAB, where TAB is the stress energy tensor. So this is Einstein's field equation, or field equations, as it's really a lot of equations all packaged into one little compact equation. And in this lecture, we're going to start investigating the general properties of this set of equations and also how to solve them. Now, it's pretty difficult to solve these equations, like it's non-trivial, and we're going to have to work really hard, and in fact it's going to occupy us pretty much for the rest of this course, the task of solving these equations in some very specific and restricted settings. So it's pretty fair to say that solving Einstein's field equations is still a bit of a research topic in more general settings. Okay, let's start with some basic properties of this equation of motion for space-time. Basic properties. What are some basic things that we can do with these equations and some basic consequences we can derive? Well, we can a good thing to do whenever you're faced with an equation of motion is just to start deriving other equations from it by operations that are allowed, and that way you'll build up a bank or library of equations that are true given that your master equation of motion is true, and then these may or may not be useful in various contexts. So the first thing we're going to do is just apply some basic tensor operations to Einstein's field equation, see what kind of consequences we can draw from basic tensor operations. So what's the first basic tensor operation you can take when you have a tensor? So on the left hand, if you look at Einstein's field equations, what do we have? Well, we have on the left hand side, we have a rank 2 tensor. On the right hand side, we have a rank 2 tensor. When you have a rank 2 tensor, you can always take the trace, contract it with a metric, and that's a legal operation. And what do you get? Well, when you trace by contracting with a metric, we obtain an equation now which relates the Ricci scalar R and the trace of the stress energy tensor. So that's a simple consequence of Einstein's field equations. So T is the trace of the stress energy tensor. Okay, and we can substitute this equation now back into Einstein's field equations. So now we're just sort of manipulating Einstein's field equations, and what do we obtain? Well, we obtain the following equation. So wherever you saw the Ricci scalar before, you can replace that with minus a pi t. And so on the left hand side, you've got the Ricci tensor, and on the right hand side, you have nearly only things that depend on the stress energy tensor. So this second equation that I've just derived here is, well, it looks very much like, but there'll be lots of warnings about this as we go through the course. It looks very much like the right hand side is just matter stuff, or energy, matter, butter, energy, matter, stress, etc. And on the left hand side there's geometry. Right, the geometry is dictated or governed by RAB. And on the right hand side, we've just got matter, but we haven't really just got right hand side matter on the right hand side. We've also got geometry in the form of the metric, at least explicitly here, and indeed implicitly in the structure of the stress energy tensor. So you can't really disentangle how the geometry is encoded in Einstein's field equations from how the stress energy and matter energy density and so on is encoded in Einstein's field equations. So I'll say more about this later. So although this superficially looks like we've just written an equation where the geometry is totally determined by the stress energy, the information is always flowing backwards and forwards in Einstein's field equations. But sometimes this equation can yield solutions. So thinking, this formulation of Einstein's field equations could sometimes yield solutions to for specific cases of extreme lots of symmetry. Okay, so now we should examine some limits. The next task in studying the properties of Einstein's field equations is to, solve it. But before we even do that, we should really convince ourselves that we do indeed recover the physics we know. In the limits where our current laws of where the previous laws of physics apply. So do we actually recover, for example, special relativity and Newtonian physics as solutions to star in some limits, or in the limits where c goes to infinity or big G goes to 0? Do we actually recover these kind of domains of physics? Do the solutions to Einstein's field equations reduce to a good level of approximation to being describable by special relativity, Newtonian physics? That's not clear at this point. Although we obtained Einstein's field equations in a kind of limiting argument, you've written down we wrote down some equations of motion. That doesn't mean that the actual solutions to these equations even exist, let alone limit to the cases where we expect them to be reducing to special relativity or Newtonian physics. So that's our goal for the next couple of lectures. And our goal is to argue that GR reduces to SR. Or Newtonian physics in the I'll just say in the correct limits, because already discussing what we mean by a limit will be slightly complicated. And we'll clarify this later. Let's start by looking at some of the consequences of various limits. So one of the simplest limits that we can investigate is the case where the energy of matter as measured by an observer at rest and I have to put scare quotes around that, with respect to the heavenly body or masses or dust or whatever. So in this limit, where if you're an observer at rest with the masses in your determining the gravitational field in your system, if you're an observer at rest with these masses, and then the distribution of energy and stress energy is such that the masses dominate the stress energy tensor, and the stresses are, you can neglect them, then in that limit, T, the trace of the stress energy tensor, is minus rho, which is also minus TAB times VA VB. And we can substitute that into our various formulation of Einstein's field equations, and then we obtain the following equation. So in this particular case, you can see that the geometry is directly determined by the distribution of stress energy. However, a warning is that this will not always be the case. Now that we've got Einstein's field equations in hand, it's probably pertinent to summarize the physical content of GR as it is in our course at the current point. Before moving on. So what is the physical content of GR? Well, firstly, there's the fundamental assumption of general relativity, plus now we've been able to write down an equation capturing the last component of the fundamental assumption of general relativity. So spacetime M, the physical content of GR is thus the following, right? Spacetime M is a manifold with Lorentzian metric. So that's an assumption. And the curvature of this metric, the curvature of GAB, is related to the matter distribution, stress energy distribution, in space-time via Einstein's field equation star. Okay, so that's the fundamental assumption as it currently stands in our course of general relativity. And even in the manipulations the elementary manipulations we've just done involving Einstein's field equations, a couple of things should really be apparent. So a couple of comments should be made that highlight or bring out certain aspects of Einstein's field equation and general relativity. And these comments have to be made at this point in the course to prevent you from drawing too strong an analogy between general relativity and electrodynamics, for example, and other fields of physics. So the first comment, it's really fundamental and you can't get rid of it, is that Einstein's field equation is not linear, right? It's not only not linear, it's highly nonlinear. It's one of the most nonlinear sets of equations that we have in physics. It's a highly nonlinear system of coupled partial differential equations. Involving the metric when you go to some coordinate system, obviously. It's not first order, like maybe the order of the derivative might be low and save you and allow you to use some computational tricks from nonlinear partial differential equations, but no, it's even second order in derivatives. So it's fiendish set of equations, and there's lots of them. They're nonlinear, they're coupled, and they're second order. So that's the first comment to make. It's really one of the most challenging set of equations of motion that exists in physics. I mean, quantum mechanics is nothing in comparison to this, right? Quantum mechanics is linear. The difficulty in quantum mechanics is there's just so many dimensions. Of course, it must be said at this point, I won't write it down, but it must be said that any nonlinear equation can be reduced to an infinite set of linear equations. So arguably the difficulty in quantum mechanics and general relativity is not incomparable. The second comment, and I've alluded to this earlier today, is that unlike, for example, in electrodynamics with Maxwell's equations, we cannot regard the stress energy tensor simply as a source. You know, in Maxwell's equations, you have the current, force current, and you can regard that just simply as a source. You specify the current, and then the electromagnetic field is just completely determined by the current, the distribution of charge and current. So we can't regard, however, in general relativity, as a source that's somehow independently causating the gravitational field, and therefore metric. There's a really fundamental aspect of general relativity that Maxwell's equations just simply doesn't have. And the reason is just defining the stress energy tensor involves the metric. Certainly in the examples that are relevant in cosmology and in even the electromagnetic field, for example. So the naive reason, and really the fundamental reason also that you can't regard TAB as a source, is that TAB, the stress energy tensor itself, is defined in terms of the metric. For most physical systems that we're going to be interested in particular perfect fluids. So we can't even interpret the stress energy tensor before solving Einstein's field equation. You have to solve for everything all at once, self-consistently. And the third comment that we have to make about Einstein's field equations, and this is the stuff of magic and awe, and that is that Einstein's field equations are amazingly self-consistent in a way that's incredibly difficult to engineer. And that is, and I'll explain what I mean. So Einstein's field equations implies this divergence condition on the stress energy tensor, right? That's in fact how I argued in the previous lecture. The modification of the Ricci tensor to the Einstein's tensor. That's one way to introduce it. And so now, okay, so what, right? But the interesting thing about this equation is that it may be argued that this equation actually implies something else, right? It implies, and this is the magic, that for a dust, right, of grains, and by that you should sort of think of test bodies. So for a dust of grains exerting no force on each other, so in the limit where you've got these little test masses, like a dust in space-time, this equation implies that the grains of sand or dust or whatever move on geodesics. So effectively, Einstein's field equations contain the geodesic hypothesis already. So I began our discussion of general relativity by saying that it's a hypothesis that observers, freely falling test masses, move on geodesics. But the equation, and then, via various argumentation strategies, we got to Einstein's field equations. But now Einstein's field equations themselves contain effectively the geodesic hypothesis that freely falling masses move on geodesics of the space-time metric. And now that's an extraordinary piece of self-consistency that comes out of Einstein's field equations. And this kind of thing is what really convinces you that there must be something right about general relativity. Usually, if you try to write down equations of motion for complex systems, usually you can write something down pretty easy, but then the minute you check it for self-consistency with other assumptions that may or may not be built directly into the equations of motion, you find that things aren't consistent. So that's an amazing consequence of Einstein's field equations, that they effectively contain the geodesic hypothesis without that being directly built into them. And that alone is breathtakingly impressive, and something that is sort of difficult to comprehend even how that came about. It's this magically wants to be correct, this theory. Okay, so with these comments in hand, let's get to the business in the rest of the course of solving Einstein's field equations. This is something we should get to now, and we won't get away from. This is it. We're going to be spending the rest of this course solving star. We're trying to, and probably failing most of the time. Of course, we're not going to completely fail. I'm going to present to you some idealized solutions. But solving Einstein's field equations in the realistic situation of the initial conditions of our universe is incredibly difficult. We can only approach its solution via various limits. And the first limit that we're going to investigate is the limit where gravity is weak. And I'll explain what I mean by that. There are other limits where we'll investigate the solutions of Einstein's field equations, and we'll be able to get a solution. That's in the cases of high degrees of symmetry in the system. So we're going to be able to solve Einstein's field equations in this situation where the universe is completely rotationally symmetric. It's not very physical, but hey, that'll get us actually close to an interesting situation to model heavenly bodies. And we'll also investigate the solution of Einstein's field equations in the cosmological setting, where the distribution of matter is uniform. So none of these limits are directly physical, it has to be said. But each of the solutions that we're going to investigate in this course will give us indirect information about how Einstein's general solutions of Einstein's field equations behave. But let's not get ahead of ourselves. We're going to try and solve, and it will take us a couple of lectures to do so. We're going to try and solve Einstein's field equations in the case where gravity is weak, very close to special relativity. Now, even this deserves scare quotes. What does it mean, weak? And for us, what it's going to mean is that the space-time metric, that's the thing we're solving for, the space-time metric must be somehow close to flat. And for us, that's going to entail an assumption, namely that the space-time metric is somehow equal to the flat metric of Minkowski space-time plus a bit, a small perturbation. And this small perturbation is going to have to be small, whatever that means. Now, in this coordinate-free notation that we've adopted here in this to describe the space-time metric G, smallness or bigness has no meaning yet. We haven't actually, you have to say small with respect to something, and actually it's a bit tricky to define this notion in the coordinate-free way, and we're not going to define it in a coordinate-free way. The only way I'm going to argue that gamma AB is small is that in a given coordinate system, in a particular coordinate system, so we're going to appeal to a certain coordinate system here, and we're going to thereby break the coordinate invariance of our equations. We're going to say that in a specific coordinate system, the components of gamma AB are small. So here now we'll be a bit more specific about what we mean by smallness. We say that gamma AB is small if there exists a global coordinate system, and I should probably say inertial coordinate system. Note the word global as well here. Such that the components of the perturbation gamma, mu nu, in this global inertial coordinate system are small with respect to 1, let's say. So, just to stress this again, before we choose a coordinate system, we can't say what gamma AB small means. Gamma AB is just an abstract box. You need a criteria for specifying when gamma AB is small or large. And the criteria that we select when discussing linearized gravity is to go to a global inertial coordinate system, the one where the flat metric is defined, for example. And now we're in a coordinate system, we can write out gamma AB in terms of its coordinate components in this coordinate system, and those will become like numbers that depend on position. Space-time position. And now those numbers, you can look at those numbers and say, are they small or big with respect to the dimensions of your, the units of your system. And now we can say a little bit better what we mean by linearized gravity. What is it? Well, it's what results from substituting from substituting GAB, let's say still, right? We understand what smallness means now, so we're going to work back in our abstract notation as much as we can into star. So that's what linearized gravity means. And collecting terms to first order in gamma AB. So there's a couple of computational subtleties that we have to highlight when working in linearized gravity. We should technically raise and lower indices with G, right? Raising and lowering is always done with respect to the metric G, but we can get away with raising and lowering with respect to eta AB because everything's small, and that works almost all the time. There is one case where it doesn't work. I'll highlight that in a moment. Let's talk about that still. There is an exception. So almost always you can raise and lower indices with the flat metric because to that order, to linear order, the higher order corrections just won't matter. However, there is an exception. GAB, when you see GAB with indices upper, that doesn't mean G raised with respect to eta, but it actually denotes the true inverse. To GAB, and not, what it could be. There's an interpretation, an alternate interpretation to what GAB could mean. It could mean, right, having raised it with respect to eta. No, we don't mean that. Whenever you see GAB with the indices raised, it means the actual inverse to GAB, and you can calculate as an exercise. In fact, it's not even an exercise, I'll just do it. GAB is, to linear order, just eta AB minus the metric. Don't believe me? Well, let's check. Let's multiply by contracting on the second index GAB upper with GAC lower. And I'm just going to collect terms to first order in gamma. Okay, so that's everything to first order that you need to worry about, and we're going to be able to neglect one term. So the first thing we get is when we contract eta against itself, and there we get a nice little delta function. And then we contract gamma against eta, and then we get this. Remember, we're using upper and lower to mean contraction with respect to eta. And then we have an additional gamma AC coming from the other contraction, and then we have a second order term, right? I'm just going to write it out, but we immediately neglect it because we're working to first order in gamma, so that's gone. And then these first order terms cancel, and so we have to first order that the equation that I've written down for the inverse of G is indeed the inverse. Now, if you're a little bit uncomfortable about raising and lowering with respect to eta AB, then you can certainly raise and lower with respect to G. You just have a whole bunch of extra terms that you'll have to worry about. But at the end, once you've done all the calculations, you'll throw all those extra terms out and you realize, oh yeah, I could have just effectively raised and lowered with eta AB. So depending on your paranoia level and your skepticism level of this statement, you're invited to go through this derivation by raising and lowering with respect to the entire metric. But I claim at the end you'll get the same result as if you just raised and lowered with respect to the flat metric. All right, so now we're in a global coordinate system, or we will eventually appeal to a global coordinate system, but we assume already at this stage that there is a global coordinate system. This is not a fundamental assumption of GR that there is a global coordinate system describing your whole space-time. Indeed, it's completely open. If our space-time is covered by a global coordinate patch, it seems unlikely with the current experimental evidence. But if you assume that space-time can be covered by a global coordinate system and that the metric gamma G is almost eta plus some small components in gamma, then you can start to calculate the stuff we need to calculate to write down Einstein's field equations. And the first thing we're going to need is the covariant derivative. And to write down the covariant derivative, we're going to need the Christoffel symbols. All right, so here we go. Let's do it. Christoffel symbols, C, A, B. How are they defined? Well, remember there's a G, CD, and then there's a whole bunch of derivatives, dA, G, BD, plus dB, GAD, minus DD, GAB. Okay, that's the Christoffel symbols, but we're working to linear order in gamma now, and now a lot of these things can just cancel out. So first of all, and I'll just do these substitutions in place. The final notes won't have this equation there, but you can see them evolve as we talk. So what's GBD, right? We had an equation for that. GBD that's the fundamental assumption of linearized gravity. It's the flat metric plus the perturbation. So we can erase G, and I'll just do that right now. We get eta BD plus gamma BD, right? That's what G is. But the derivative of the flat metric is 0 because it's just a constant. So actually, to linear order, G vanishes and we just get gammas instead. Okay, that was easy, right? We just got rid of a bunch of terms. There could potentially have been, 6 terms in the brackets here. No, there's actually only 3, thankfully. And now we've also got the inverse of the metric, right? So, but I told you how we're going to compute the inverse of the metric. That's going to be computed as eta AB minus gamma, eta CD minus gamma CD. Now, already, we get to throw away some terms because the stuff to the right here, OneNote crashed. Okay, the stuff to the right here, just check the recording is working. The stuff to the right here is already at linear order in gamma. And so if you multiply anything at linear order in gamma by something at linear order in gamma, namely gamma itself, then you get 0 to linear order in gamma. So actually, we can compute the Christoffel symbols, somewhat easily. Well, less horribly than maybe could have been the case. And so now we've got an equation for the Christoffel symbols, right? We can just dump this equation that are in red that I've struck out to 0, and we're left with a somewhat simpler expression for the Christoffel symbols. And that now, once you've got the Christoffel symbols, you can just go straight ahead and compute the Ricci tensor. If you remember when I introduced the Ricci tensor, there's a way to compute it in terms of the Riemann tensor. And in our case, the Riemann tensor is just some expressions involving the Ricci tensor, derivatives of the Christoffel symbols and quadratic expressions in terms of the Christoffel symbols. So this is an exercise for you. And the claim is to linear order the Ricci tensors actually, you can find it via this equation here already. You remember, you would usually have some terms involving the Christoffel quadratic expressions of the Christoffel symbols, but they all vanish to linear order, right? Because everything's already to linear order. And so if you square them, then you've got to get 0. So there's the Ricci tensor, and we can now substitute for the expression that we have obtained for the Christoffel symbols just above to linear order, and then we get C, and then there's some symmetrized terms. Oopsies. Where I've introduced the trace of gamma. Gamma is defined to be the trace of gamma. Now that we've got the Ricci tensor in hand, we can write out the Einstein tensor, GAB to first order. And the way GAB is defined, well, you take the Ricci tensor and you subtract from it a half by the metric multiplied by the Ricci scalar. Now to this level, to this order, we can regard the metric simply as its linear term because the other term multiplied by the Ricci scalar is already 0 to linear order. And we obtain the following lengthy expression for the Einstein tensor. Things will simplify later, but at this point, this is what the Einstein tensor looks like. We can make things look a slightly bit more compact. By defining a new quantity, gamma bar, the perturbation, as being minus a half, as gamma AB minus a half eta AB times by gamma. And then then star Einstein's field equations to linear order, Einstein's field equations now can be written out in their full glory, and here they are to linear order. This is just an exercise in rewriting some equations for you, and the right hand side is just the full stress energy tensor. So this is what the Einstein field equations look like to linear order. We haven't done anything particularly intelligent yet. We've just substituted our expansion for the metric into Einstein's field equations, collected terms to linear order in gamma, and written out what we've got. Now, this equation is not super friendly to look at. Actually, have I missed a term? 1, 2, 3. No, that's correct, I believe. This equation is not super friendly to look at. I mean, it is linear. It's linear in gamma, right? And so at least we have a chance of solving it. When something's linear, it's a linear PDE of second order in gamma. And so we can go ahead and solve this set of 16 linear PDE. But you want to work smart when you can, and we're going to do that now. We're going to take a digression for the next lecture or two to actually identify the symmetries of this equation so that we can simplify it somewhat. It'll make just our lives easier. And so we're going to make a little bit extra investment of energy now in understanding the symmetries of this equation so that we can spend that symmetry to write down a simpler equivalent equation for gamma. And that equation will be so simple that we'll be able to solve it really easily. So that's our task now. So this equation, you can actually simplify it. And the way you simplify it is to use the gauge freedom, so-called gauge freedom, of general relativity. So general relativity, the formulation that we're describing here of general relativity has a symmetry. And I'm going to explain that symmetry over the coming lectures. And it is this, that if you have a diffeomorphism phi of your spacetime manifold M, then the two metrics, namely your original one that solves Einstein's field equations, and the metric you get from doing the diffeomorphism, we'll call it GAB prime for the moment. I'll explain how to calculate GAB prime. They represent the same space-time geometry. Now I'm going to explain all of this. But to do that, we're going to have to spend a little bit more time on some foundational aspects of differential geometry. Okay, so we're going to take a little digression to talk about maps of manifolds. So let's suppose that we have two manifolds, let's say M and N. They're arbitrary, right? M and N. And let's also suppose we have some map between these two manifolds. Let phi M and N be a smooth map. from m to n, then the first thing to note is that associated to any function on our target manifold n, given any arbitrary function on n, there's actually implicitly via phi a function on m. A so-called pullback function f composed with phi, and if you check where the arrows go, everything works out, right? So here's, this is the manifold m, then we have the map phi from m to some other manifold n, and then you've got a map f to the real numbers, and then just by doing one then the other, you automatically obtain a function that goes from m to r. And this function has a name, it's called the pullback function. Now, it doesn't stop there. The minute you write down a map between two manifolds, then you can start pulling back various geometrical quantities from one manifold to the other and pushing forward other ones. So let's talk, what kind of geometrical quantities am I talking about? Well, the first associated quantity you can put on a manifold after functions is tangent vectors. So what happens to a tangent vector? Well, if you have a tangent vector, suppose you have a tangent vector at some point P in M, there is you can actually build in a canonical meaning standard, there is a so-called push forward that you can define canonically on n. And the way you obtain this push forward vector is we set up first a linear map phi star that takes the tangent space at some point P in a manifold to a tangent space defined at the image of this point. So this is the point P, and under phi we have another point P, phi of P here. And we obviously will eventually get an image of the tangent vector at P. And how does this linear map work? Well, phi star is defined as follows. So for some tangent vector at a point P on the manifold M, we're going to define a new tangent vector, phi star v, which lives at the corresponding point phi p in the manifold N, by this formula here. Phi star v, when evaluated on a function f, is just to be defined to be v evaluated on f composed phi. You should think about this for a bit. There's a couple of properties that you need to check that this definition is coherent with. Do you get a tangent vector? Is it linear? Does it obey Leibniz and so on? And that's got to be true for all smooth functions on M. So we get a tangent vector by this prescription here, and this is called the push forward of the tangent vector v. Now it turns out the map phi star is familiar to you. It's the Jacobian. If we choose a coordinate system, so if x mu denote coordinates of M, respectively y nu is the coordinates of n, then the matrix, because now, you know, phi star is a map of linear vector space, is a linear map of vector spaces, phi vp to v phi p, so you can write it out as a matrix in terms of a basis of both of these vector spaces. So, and that basis is furnished by the standard derivatives with respect to these coordinates. So the matrix of components of phi star is then so this, you know, you can now regard it as a matrix and you can work out its components, and this is an exercise for you to just confirm this, is dy mu dx nu. So phi star is the Jacobian, if you like, of the map phi. Now similarly, right, this is, now we've got it for vectors, we can immediately start deducing things for covectors or dual vectors by the same argument. So we can pull back dual vectors at phi p. By defining the following linear map going from dual vector spaces v phi p star to vp star, and how do we define v phi star? Well, give it a dual vector mu, and then demand that when we contract it with a tangent vector v, that's the same as applying the dual vector to phi star v contracted against mu. So that's how you can immediately extend, you know, the minute you have something that maps tangent vectors, some tangent vectors in one vector space to a tangent vectors in another vector space, then you pretty much have something that'll hold dually for the dual vectors. And we can extend this now to even tensors of type T naught L. By defining phi star of a tensor, the components of a tensor, by demanding that these components phi star of t obey the following equation here. And this is just the generalization of the push forward equation that we've already seen. Sorry, the pullback equation. And to tensors of type k naught, we also have a similar push forward type expression. This is what you get. It's essentially natural. There's no way you would have a hard time arguing that this is not the right way to do things. So this is for all v1 through to vl and for all mu1 through to mu k. So once you've got a map between two manifolds, then very quickly you can build maps between tensor objects on these manifolds. But note the directions of these arrows, right? So here's M, here's N. So phi star, the push forward, goes that direction, and takes tangent vectors forward, but phi star lower goes the other direction. Let me just check that that's consistent with what I've been saying. Yes, indeed it is. So, and that means that a tensor object which is acting on n and is some tensor products of the dual vector space, a tensor object there gets taken back to M, but a tensor on vector spaces, or in tensor products of vector spaces, tangent vector spaces, gets pushed forward to n. So there's no natural way to get an action of phi on mixed tensors. Because the arrows are going the wrong way, right? Some of the components get transformed from mapped from n to m, and some of the others would get mapped from m to n. Yeah, so we don't get an action on tensors of type KL. There's no natural action on tensors of type KL because a tensor of type KL, the various components will be pushed forward or pulled back depending if they're vectorial or dual vector. But there is a way to get out of this. If phi, so far phi is just some smooth map. It doesn't have to be any particular smooth map. However, if phi is a diffeomorphism, then we have a little bit more information that we can exploit. And in particular, that means that M, the manifold M, is now the manifold N. So if phi is a diffeomorphism, we can exploit the fact that the inverse exists and is also smooth. And we can extend this map that we've just defined above to apply to mixed tensors. And this is because phi inverse star is a linear map that goes from v phi p to v. So now that takes vp, that takes the vectors on the target manifold backwards. And then we define, in this particular case, a full action of phi on a mixed tensor. And how do we do it? Well, we just combine the two actions that we introduced above. May as well put V's here. So we take these actions of phi star on the individual dual vectors and vectors, and we apply them to the inverses now of phi also in order to get a map that goes the correct way. And that in turn has allowed us to define an action of phi, and implicitly thereby of course phi inverse, on mixed tensors now. And of course there's a implicit here, in order for this to be well defined, is the fact that phi star has got to be equal to phi inverse star. You better check that. It's important for things to be correct. Okay, and so the final definition I'll make before finishing up today is to isolate the special role played by certain diffeomorphisms in general relativity and in differential geometry. So there are special diffeomorphisms phi, namely those that are such that the metric is invariant under applying diffeomorphism. those, now we can actually write down that expression. What does it mean for the metric to be left invariant? Well, you need to have an action of the diffeomorphism on the metric that we've just obtained above. And therefore there are a special class of diffeomorphisms which leave the metric absolutely alone, and those are called isometries. So these symmetries are the fundamental symmetries of space-time. However, the symmetries of general relativity are actually much larger than just isometries, because it'll turn out that diffeomorphisms are in fact will yield identical manifold structures, and that general relativity is written in terms of coordinate-free expressions of the metric, so that when you apply a diffeomorphism to a manifold, you actually get when you look at physical quantities, you'll find that they lead to they'll lead to operationally identical predictions. So the actual symmetries of general relativity will be diffeomorphisms, but we'll talk about that in the next lecture. For today, that's it. Thank you very much for your time, and see you next time.